Hello everyone, welcome back to our channel Maxco Tech. You are watching series Graph Theory. This will be a series of videos in which you are going to know everything you need to know about graphs, including their definitions, where are they used, and what type of graphs we have, vertex degrees, what is a matrix is. We'll also be looking at directed and indirected graphs connectivity and reachability, weighted graphs, trees, and spanning trees. So, a lot of things to cover, so buckle up and let's get started. In the very first video, we will introduce ourselves with the definition and the types of graphs, vertex degrees, and matrices. A graph helps us to understand and architect the census nodes layout easily by providing us the higher level of the visibility of entire network. A graph G represents nodes and the distance between other nodes by using vertex sets V and the edge sets E. For example, in a network of 6 nodes, our vertex set V of graph G is a set of vertices V1, V2 till V6. Note the difference between the capital and the small v. Similarly for edges E1, E2 till E6 that are connecting two vertices, every edge is a tuple of two vertices represented as follows. Now where would you see the application of graphs? For example, knowledge discovery in social networks, for example, who is linked with what, targeting advertising, pattern extraction for behavioral analysis, useful statistics and conclusions for a wide range of scientists, mining in web data, interesting navigation patterns, XML documents, biological data analysis, drug discovery by finding out the DNA analysis in the proteins involved, geographical information systems, security, finding possible connections between the suspects, and of course the transportation maps can also be modeled as a graph. A neighbor set of vertex V in a graph G is a list of all other vertices that are adjacent to V, means they are connected to V by an edge E. More formally, for any graph G and a vertex V, which is a subset of vertex sets capital V G, the neighbor set capital N V of the vertex V is the set of vertices other than V adjacent to V. As an example, looking at the neighbor set of vertex V2, we have V3 and V1 adjacent to it. Hence, the neighbor set of V2 is V3 and V1, which is also a subset of graph G. We will study the subsets later in this video. Total number of edges incident on vertex V is called vertex degree, such that the maximum degree of the graph G denoted by delta G is 5 on the vertex circled red, and the minimum degree on the graph denoted by gamma G is 1 on the vertex circled green. Note that the edge joining with its own vertex, in this example E7, is known as a self loop and is counted twice. Let's say for the vertex at top, its degree is 2. So that means the total vertex till now are 4, because these edges are also connecting with two other different vertices. So counting all edges of each vertex in a graph would result in twice the number of edges. Hence, we can safely say that the sum of total degrees is always even. If it's not, then the graph is not properly structured. In other words, for any graph, the sum of degrees of the vertices equals twice to the number of edges. A simple graph is the one which has no loops. Graph on the right has a loop from V1, V4, V5 and back to V1. So breaking the loop would result in a simple graph. A simple graph should also have no multiple edges between each pair of the vertices. A regular graph is the one where every vertex has the same degree, called k-regular graph, where k represents the common degree. The graph in our example on the right is also called k-regular graph with k equals 2. Complement G prime of a graph G is the one that has all the vertices of a graph G and all such edges which are not in the graph G. More formally is represented like this. So let's say this is our graph G consisting of 5 nodes And this is the complement of the graph G. Now, a complete graph is the one that is created by taking the union of the graph G and the G prime, shown on the right, where we can see that every pair of edge is connected and every two vertices have a direct link between them. A subgraph H whose vertex sets and or edge sets are one from those of the original graph G. More formally, we can also call it as H is a subgraph of G if the vertex sets of H is a subset of the vertex sets of G, and the edge sets of H is the subset of the edge sets of G. Induced subgraph G dash whose vertex sets and or edge sets are one from those of the original graph G such that all of the edges connecting pairs of vertices in that subset exist. As we know that the graph in the center is the subset of G, but it is not induced subgraph of G because it does not contains all the edges of the shared vertices. The shared vertices are A, C, E, and D, where the edge from A and D is missing. Also from C to E. So the graph on the right is induced subgraph of G and is induced by A, C, D, and E. Each number of matrix shows if the pair of vertices are adjacent to each other. Taking an example of V3 and V4, which have two edges E2 and E8 respectively, let's look at the E2 first and mark the number of matrices from the x-axis so that V3 connects with V4 by an edge E2. So we will mark this box as 1 initially. Now looking at from the y-axis, V3 is connected with V4 by 1. So we will mark this as 1 initially. Since we need to repeat the same for another edge E2, which is connecting the same vertices, we will increment both of these numbers by 1. So hence they make it 2. And similarly, we repeat for all of the vertices from both axes and make the connections, and hence marking the rest of the empty boxes as 0 in the matrix. You may note that adjacency matrix is symmetric. By I and j, I am referring to the index of the matrix. For example, if I is 0 and j is 1, we are referring to A01, which is the 0th column and the first row, which makes it 1. So I01 is 1, which is equal to I10. A graph is simple if and only if the arcs I and j, referring to the gray and the green area in the matrix, are 1 or less than 1, but are not negative. And AII, which is referring to the center line in white, is 0. Incidence matrix. They also represent the graph in the form of matrix. But this time each number of matrix shows the vertex pair connected with edge. So on the y-axis we have vertices, whereas on the x-axis we have edges. This is quite simple to form by making 1 on the each edge connecting two vertices. For example, in the first column E1, V2 and V3 are connected. Similarly, V3 and V4 are connected by E2, and it goes on till the last edge is 8. Note that the vertex V5 is counted twice on edge 7 because that is a self loop. And mark the rest of the empty boxes as zeros. Graph isomorphism. So the two graphs G1 and G2 are isomorphic if there exists one-to-one mapping for each vertex. In simple words, if the two graphs visually look different but they have same matrix, then those two graphs are isomorphic. For example, the simple one is on your left and a bit more complex on your right. I have just shuffled their positions of the vertex. That is all we are going to cover in this video. In the next one, we are going to look at the connectivity and the reachability of the graphs. So stay tuned and don't forget to like and leave a comment if you have any comments. And if you are new to this channel, please don't forget to subscribe us. So I will see you in the next video. Thank you so much.